Hi, my name's Hannah Wesselman and we're going to be doing a photosynthesis lab today. So earlier I cut out some spinach leaves with a hole punch and just made little holes in them. So I already have one set up. So we're going to try to figure out what factors play a part in photosynthesis. So I'm going to take those spinach leaves, they kind of fell off, sorry, and put them in a syringe. And when we're doing this, we're going to see what color of light affects photosynthesis. So I have one already set up that has green, clear plastic wrapped over the syringe so that only green light will affect these spinach leaves. And in this one we're going to put red light. Those really don't want to go in there. So, in with the spinach leaves, we're going to put a mixture of water, baking soda, and a little bit of soap. So the purpose of having the soap and the baking soda in there is that in our equation of photosynthesis, it's H2O plus CO2 yields glucose, C6H12O6, and oxygen. So, with the water and just the spinach leaves, there would be no source of carbon dioxide. So that's really important in photosynthesis. So I've already mixed this up in here, so we're going to add about 15 milliliters of that mixture to our syringe and make sure that all the spinach leaves are in that mixture. And then we're going to make sure that we get all the air out so that there's no outside source of air or carbon dioxide other than the baking soda that we added. And there's going to be little bubbles in the top, but you can just push those out. And it's okay if a little bit of the liquid comes out with it. Okay, so now we have all of our spinach leaves and they're all floating at the top. So now what you want to do is make them sink. And so you're going to take all the air out and that's going to make them go to the bottom. So just put your finger over the top of the syringe and pull down. And make sure that when you do this, that all of the spinach leaves stay in the solution. So you might have to shake it a little bit to make sure that they don't get stuck on the sides. So just pull down really slowly, and then release, and they should sink. So now we have all of our spinach leaves at the bottom. And so you might get a little bit more air, so you might need to squeeze it one more time to make sure that all the air is out of there. So now we're going to add our plastic cover over the top of this syringe, and we are ready to go. Alright, now that we have both of our syringes set up with the colored paper over the top, or the colored plastic rather, we have these heat sinks set up. That way, for both of these, we want the color of the light to be what affects the rate of photosynthesis. And so if we were to take that water away, then the heat from the lamp would be affecting the rate as well. So that's a way that we can just take that part out of the equation. So in our equation for photosynthesis, oxygen is produced. And so that way, when these spinach leaves start to float, the oxygen gets trapped in the epidermis of the leaf, and that way they float. And so that's what makes them rise, and that'll be what tells us which color light is going faster, which rate of photosynthesis is going faster. So we're going to start the timer for both of these. I'm going to turn on the lamps and start the clocks. And when 50% so 5 out of the 10 of the spinach leaves has risen to the top, we'll stop the clock and record our data. So at the conclusion of our experiment, our spinach leaves with red light had about 50% risen to the top at 9 minutes and 40 seconds. We just passed about the 30-minute mark of the green one being in the light, and still none of them have risen to the top. So we're just going to call that void. So why did that happen? If we look at our graph here, so chlorophyll and other light-absorbing dyes and things that are in plants only absorb certain wavelengths of light, and that relates to rate of photosynthesis. So from about 400 to 500, the rate of photosynthesis is really high because that's the high absorption rate. So from 400 to 500 nanometers, the chlorophyll can absorb a lot of that light. From about 500 to 600 or 500 to 650, the rate of photosynthesis is really low, and that relates to our green light here. So 500 to 600 has a green tint or a green light, and so plants are green because that's the light that they don't absorb, that's the light that they reflect. So that's what gives plants their green color. From 600 to 700, we have a really high, once again, a really high rate of photosynthesis because the plants are absorbing a lot of that light. So that's why when we have 50% risen up at such an early time compared to our green, that's why the red was so successful in performing photosynthesis, because that oxygen was able to be trapped in that epidermis from from performing photosynthesis. And with oxygen being one of our products of that reaction, that oxygen that's given off, that air that's given off, is trapped inside that leaf, and that's what makes them rise to the top. So when we look at our graph, it kind of explains why, not only why plants are green, but why certain lights help plants to perform better in creating their own food. So I hope you learned a lot, and I'll see you guys next time.